Hi everyone, I am Supratha and welcome to week 6 of live session for the course Fluid Dynamics for Astrophysics. Um, Let us start by recapping what was done in this week's lectures. So this week was all about shocks. Um, Shocks are, as was discussed in the lectures, these are discontinuities that tend to develop in supersonic flows. Uh, So these are discontinuities in parameters like pressure, density, and velocity flows. Uh, and the way they form is basically if you have a supersonic flow, and let's say you have a pressure pulse like this, uh, the velocity in the top part is tends to be more than the velocity at these points, and the pulse is modified to take this shape. It can technically take, mathematically, it can take the shape as so, but of course, if you ask somebody what's the pressure at this point, then one can basically say, well, one doesn't know because there are three values corresponding to this point. So what we say is, well, the pulse is modified to a shape like this, and this discontinuity develops. Now, ideally, this discontinuity, which is the change in the value of pressure density, occurs abruptly at a point. But in real life, this is not the case. And essentially, what happens is you have a very small but finite thickness of this shock. So the profile looks more like this, where you say that this is the shock front, and of course this is the zoomed in version. This is supposed to be much smaller. How small or what determines the thickness of this shock front? That was also talked about in the lectures. So the point is, if you are studying a fluid which is essentially inviscid, so this viscosity parameter, coefficient of viscosity, is quite small. Uh, but near the shock, what happens is you have a discontinuity in the velocity, which means that there's a sudden change in the velocity over a very small length scale. And these length scales are so small that if you calculate the second derivative, it's the Laplacian of u, which is d2u dx2, this is a very small quantity. So even though mu is small, at the shock, d2u dx2 is so large that this quantity, which is the viscosity, the term which accounts for viscous effects in the Euler equation, this term in the Navier-Stokes equation, this term is quite large. So it's no longer so the viscous effect is no longer ignorable near the shock front. So near the shock fronts, what happens is for steady flows for steady flows, the viscous effects tends to be comparable to the inertial term. And for steady flows, the inertial term, which also had a del u del t, this term is ignored for steady flows. So you equate the second term in the inertial component to the viscous effect, and this gives you this equation. So you see, this basically tells you that you have a du change in velocity over length scales dx, and dx is the thickness of the shock front. And that is what we wanted to compute. We wanted to get an estimate for the thickness of the shock front. So if you write dx as delta, which is the shock front, and du as u, considering that this is the velocity which abruptly goes to zero, let's say, over as you go to the other side of the shock front, uh, and you substitute this in this equation, you get an expression for the thickness of the shock front. And this is given by nu by u. This tells you that if you have an ideal fluid, then you will have an ideal condition where the thickness of the shock front is exactly zero and the discontinuity is ideal. But that's not the case. Nu is essentially very, very small. So smaller nu, which means the less viscous the fluid, the thinner the shock, the sharper the shock, right? And the faster the fluid flows, the thinner is the shock. Okay. Uh, Next, what you do is you figure out the dimensions of nu, turns out to be centimeter square by second, which is almost the same as, not almost the same, which is the same dimensions as lambda times the RMS particle velocity, the particles which constitute the fluid parcels, right? And this was also discussed that URMS and speed of sound, they're almost the same modulo a few factors. So you have a factor of root gamma in CS and you have some factors, some three or something, depending on what sort of gas you're considering. So modulo a few factors, mu is essentially lambda, which is the mean free path, times CS, which is the speed of sound. Now, if you're considering mildly supersonic, by mildly supersonic, I mean the Mach number is not much greater than 1. So let's say you're considering Mach numbers close to 1, but greater than 1. Mildly supersonic, steady flows. Then Mach number close to 1 tells you that you're considering a situation where the inertial term is comparable to the pressure gradient term. Because the Mach number is, remember, the ratio of inertial term to the pressure gradient term. Okay? This tells you that this holds true. Because you're considering steady flows, the del U del T term in the inertial contribution to Navier-Stokes equation just drops off and you just have rho u du dx. And on the right hand side, you have the pressure gradient term. Substituting dp dx with dp d rho, or rather del p del rho. And this has been done a million times over and over. This is cs squared, the speed of sound squared. You get this, and ultimately this equation turns out to be u equals cs. And remember, so u, which is, remember this time u is the velocity of the fluid parcel, is also comparable to the speed of sound for mildly supersonic steady flows. So what do you get? You get this this capital lambda, which was the shock thickness, which is almost equals to nu by u, and u, as we discussed, is equals to the velocity of the fluid parcel is comparable to the speed of sound comparable to the RMS velocity, and so on. You just substitute this over here to get this, which is lambda. So the essential point to carry from this is that the shock thickness in real life is almost is comparable to mean free path. A few modulo, a few factors. Okay. Next, what we will do, what will take most of our time in this slide session is deriving the shock jump conditions, because that was left as an exercise in the lecture. So we will derive this in today's session. Okay, so first let's review what we are actually going to derive. Okay,
Excuse me. Actually, my question is, why are we being so imprecise while deriving this shock thickness thing? Like, we are always taking approximations here.
that's the best we can do. What we want to do is we want to get an idea of, let's say, we want to know why should we have non-zero shock thickness. We understand that this exact shock thickness being zero or an ideal discontinuity, it's something we don't expect to see in real life. So what is a good or what can how can we look at the microscopics and then conclude, well, this is the parameter that will tell us how small the shock thickness is going to be. I know it's imprecise, but for now, if we don't want to complicate our lives, if we don't want to complexify it, then this is the best we can do. And I think it's a nice uh, way to understand or compare situations. Let's say you want to shock honey versus water. How easy will it be to, or which one will be easier to shock, right? Things like this. I think it's nice to have a very rough zeroth order understanding of where this is coming from. Where is this finite thickness of shock coming from?
Okay.
Okay. Okay. Uh, so uh, there. was a possibility of getting upstream and downstream confused when discussing about these shock jump conditions. So let me just very quickly recap. So let's say you have fluid over here. Let's say you develop a discontinuity. Let's say you develop a pressure discontinuity. Okay. This is the shock front. This is the discontinuity. Now, so this shock front divides the entire fluid into two zones. Zone 1 is what we call the upstream zone. The upstream zone is the pre-shocked fluid. So we say that our shock front is moving in this direction, or let's not, okay, forget about that. Our shock front demarcates our entire fluid, divides our entire fluid into two zones. The first zone is the pre-shocked fluid, okay? So this is the fluid that is ahead of the shock and has not been shocked yet. The shock front has not passed through this zone, has not affected fluid in this zone. This is the upstream zone. Zone 2 is the post-shocked fluid. So the shock front has already affected the fluid over here, and the fluid moves away from the shock front with certain velocity u2. The density and pressure in zone 2 are denoted by rho 2 p2. The density, pressure, velocity in zone 1 is denoted by the subscript 1, and fluid in the pre-shock fluid moves towards the shock front to be shocked by this velocity with this velocity u1. I hope upstream downstream is clear now. Okay. Uh, so right. So what the shock front does is it converts regions in zone 1. It converts fluid parcel in zone 1, which we will see are supersonic. We will derive jump conditions and we will see that the fluid over here is supersonic. Hmm? And what this shock front will do is convert this fluid from supersonic to subsonic, convert flow in this region, in this zone, from supersonic to subsonic. So we'll derive jump conditions. To do that, what we will do is we will look at fluid considerably far away from the shock front, such that we can keep working with the inviscid approximation. Remember, we are working with fluid which has zero viscosity, but as discussed, near the shock front, viscosity becomes important because velocity has large gradients across a very short length scale. So the viscosity term starts becoming important, but away from the shock front, since mu is small, we can effectively keep working with the zero viscosity approximations. Okay. So what we do is we write down mass, momentum, and energy conservation equations for fluid in the two zones. So the mass flux conservation tells us that rho times u in the two zones will be equal. Euler equation, we have the Euler equation and we have the energy conservation equation, where W is supposed to be the enthalpy. So this is the kinetic energy of the fluid parcels, which is due to the bulk motion, and this is due to pressure, temperature, the internal energy of the fluid. Okay. Once we have these three equations, we understand that there are six variables to solve for. So what we instead do is we solve for ratios of these variables. That gives us the jump across the shock front in these variables, in the variables u, p, and rho. Okay, so we will rewrite the energy conservation. Now in the lectures, this expression for the enthalpy was used. Let me tell you why this is correct. If you remember, this is nothing but the Bernoulli's equation, which holds true for inviscid fluid, inviscid flow conditions, zero viscosity flow conditions. So in Bernoulli's equation, if you remember, this term was basically integration over dp by rho. Now this is basically equals to this because p is rho times rho to the power gamma. dp is gamma rho to the power of gamma minus 1 d rho. So W, the enthalpy, W, the enthalpy, is integration dP divided by rho, which is basically this. You integrate this to get this. Now you rewrite rho to the power of gamma minus 1 as rho to the power of gamma divided by rho. Rho to the power of gamma is P divided by rho. So this is enthalpy. Now what we will do is we will derive this that was left as an exercise. This is the jump in the density across the shock front. Okay, now I'll take you through the steps because, and it can be tedious, but there are some sleek results, so bear with me. What we will do is we will take Euler equation and we will divide both sides by rho u. We will divide the left hand side by rho 1 u1. We will divide the right hand side by rho 2 u2, and they will be equal because rho 1 u1 equals rho 2 u2. So we take the Euler equation, we divide it by rho 1 u1, rho 2 u2. Okay. You break this apart. The first term will give you 1 by rho 1, p1 by u1. Now p1 by rho 1, you can substitute as 1 by gamma cs1 square divided by rho 1, divided by u1. The second term is just going to give you u1. Same on the right hand side. Same thing. Where cs1 square, this is the speed of sound in zone 1, which is the pre-shocked zone. Remember, zone 1 is the pre-shocked zone. Shock has not affected this yet. Zone 2 is the post-shock zone. Okay. All right. Okay. Now what you do is you take u2 to the left hand side and you bring this term to the right hand side and you get this. You keep it as it is. Now we will use the third equation using this expression for enthalpy. We plug this in over here and we write down the equation, which is this. Okay. We once again substitute gamma p1 by rho 1 with cs square and write this down. And we do the same thing over here. Now understand that this is equals to this is equals to a constant because this quantity is conserved, right? So we write down a constant on the right hand side. Notice that for a give, once you know what the fluid is, you know what gamma is. Gamma is a constant throughout the flow. Let us write the right hand side, which is a constant, as this, where lambda is some constant. We could have written the right hand side to be some a square instead of writing it or some constant b. We are just writing a constant on the right hand side. Lambda is a constant. Okay. Then what we can do is we can equate this to this and write cs square as this. Similarly, using this equation, we can write cs2 as this. Okay. Now, you have a cs2 square and cs1 square in this equation. Remember, this equation is what you derived by dividing the Euler equation with rho 1 u1, rho 2 u2. We will use this expression of cs1 square cs2 square in this. What we will get? We will get u1 minus u2 equals to, substituting this expression, we have this. Substituting cs1 square, we get this. Rearranging, just rearranging, we collect this term, write it down with this term to get this, and we collect this term and write down this. Okay. Now you can see that this will become u1 minus u2 divided by u1 u2. u1 minus u2 will cancel out and we'll be left with a 1 by u1 u2. if we do this, we will get this equation. All right. So 1 by u1 u2, 1 by u1 u2, bringing all the other terms to the right hand side, we get this. Now if you solve for this, you will see that this is gamma plus 1 by 2 gamma. 2 gamma, 2 gamma, 2 gamma, 2 gamma cancel out. Gamma plus 1 cancels out. This should be 1 by lambda square. So what did we get? u1 u2 equals lambda square. To remind you, lambda was just a constant that we defined over here in the energy conservation equation. Okay. So what do we get? We get that the product of the velocity pre and post shock is equals to some constant. This is the Prandtl condition, and we will be using this. To remind you what we were originally doing, we wanted to derive this jump condition. We are almost done, so bear with me. Okay.
Actually,
Again,
what is the point of putting a square over the lambda, because lambda is just an arbitrary constant.
it is an arbitrary constant. Of course, what there was no also no point of doing this. This is just convenience. You will see. You will see.
Okay.
Just to avoid factors of just to avoid square roots and so on. And also these factors nicely cancel out, you will see in these expressions. That's why we defined the constant with this. And this lambda square comes because we want to avoid a lot writing down square root a lot of times. Just convenience. Okay. Again, remember this expression, okay? So this is equals to this. Let us write this down again. Okay. Now let us divide by u square, both sides. We get this, we get this, and we get this. Okay. Let us add this. We get this. From this equation, we can find out the inverse of this. So u square by lambda square just turns out to be this. This cancels out. The denominators cancels out. Gamma plus 1 goes to the denominator. And then you invert this fraction to get this. Okay, we're almost done. Now remember from the mass flux conservation equation that rho1 u1 is equals to rho2 u2. So rho2 by rho1, which is what we originally wanted to calculate, the jump condition in density, rho2 by rho1 is equals to u1 by u2. But remember, u1, u2 are related to the u1, u2 is constant. So what we do is we multiply numerator and denominator by u1 to get u1 square by u1, u2. u1, u2 is lambda square. Okay. So rho2 by rho1, which is u1 square by lambda square, and using Mach is equals to this, we get this. Because u square by lambda square is equals to this, right? So we write down this. So what do you get? You get rho2 by rho1 is equals to this, which is gamma plus 1 by gamma minus 1 plus 2 cs square by u1 square. But we are now using the relation that we are defining this mathcal as u1 square by cs1 square. So this becomes 2 by m. This becomes 2 by m.
But shouldn't that be Mach number squared? Like
Yeah.
us.
You are actually right. Yeah. I made a mistake. You're right. Mach square. You're absolutely right. So this becomes 1 by Mach square. You multiply both numerator and denominator with Mach square to get this. Okay. This is exactly what was asked to prove. We were asked to prove the inverse of this, and we have proved that this is the jump condition. Now, using the mass flux conservation, we see that rho 2 by rho 1 is u1 by u2. So we've also derived the jump conditions on the velocity. Now, notice one thing, that for large m, this will asymptote to some number because you have m squares in both numerator and denominator. For large m, this will asymptote to a number. Okay, and this plot was shown in the lecture. I hope you can recall. Uh, Here you see that on the x-axis you have Mach number, which is this m, and on the y-axis you have various quantities plotted. What we have derived over here is rho 2 by rho 1, which is basically this, and the jump conditions and the velocity, which are plotted over here, right? And you see that for large m, rho 2 by rho 1 essentially become constant. They don't change with Mach number. Post a value of m equals 4. Okay. What was not derived was there's also you can also derive conditions, jump conditions on the pressure, and that will come quite easily once you know this condition. So you write down the the uh, the momentum conservation equation, and then you will divide the left hand side with rho 1 u1. We repeat the trick. We divide the left hand side with rho 1 u1. We divide the right hand side with rho 2 u2, both being the same, and we get this. Okay. Rearranging the difference in the pressure post-shock and pre-shock turns out to be this. We divide both sides with P1 to get this. Now, over here we once again repeat the trick that P1 by rho 1 gamma is Cs square, right? So we had a rho 1 here. We divided this by P1. We rewrite rho 1 by P1 as Cs1 square by gamma. And we pull out a factor of u1 to get u1 square, and this becomes 1 minus u2 by u1. Okay, so remember this was the Mach number square, so we write this as gamma m square, and we know what u2 by u1 is. That is something we derived over here. So we substitute for this ratio by this term. Simplifying this, you will get this. So you bring this minus 1 to the right hand side and you get the jump conditions on the pressure. So what we see is that this actually does not asymptote with large Mach number. It actually increases as m square. And that is also visible in this plot. Okay. What you can also do is derive temperature jump conditions across the shock front. That is easy to calculate because P is rho at T, right? So T2 by T1 will be P2 by P1 times rho 1 by rho 2. And we know P2 by P1, it is this. And we know rho 1 by rho 2, it is this, inverse of this. We bring everything together to get this. And once again, you see that this increases as m square. There's Mach squared in numerator and denominator for this term, but this term goes as m square. So the temperature jump is also increases as m square. It is not asymptote. And that is also clear from this graph. Okay. The nice part about these jump conditions is they all depend just on Mach number. Once you know gamma and the Mach number, once you know what fluid you're working with, as well as the Mach number, you can derive the jump conditions across the shock front. Okay, I hope this idea of downstream and upstream was clear. Which is which? A nice way to think about it is this. The shock we said develops because the pressure pulse, think about a pressure pulse and think about rho equals constant. This is uh, just for your understanding to be prepared with to be prepared with what is going on. We know that a pressure pulse is modified to this discontinuity, right? Now, if this is the shock front, if we treat this as the shock front, because this is the discontinuity, shock front is nothing but the discontinuity that is moving along this direction, then fluid on this side of the shock front moves towards the shock front in this direction, and fluid moves away from the shock front along this direction. So this is the shocked zone, which is basically zone 2, and this is the unshocked or yet to be shocked zone, which is zone 1. Okay, which is basically just this situation inverted laterally. Huh? And that is exactly what you will see, because you will see that P2 by P1 is greater than 1 and it increases with Mach number. P2 by P1 is greater than 1 and it increases with Mach number. So you see that uh, this is the intuitive way to understand this. This region is the unshocked region, and this region is the downstream region. The region, the fluid in this region has already been shocked, has been already been affected by the shock front. Okay. Uh, then something called transonic flows were discussed. Uh, transonic flows are flows that will continuously or smoothly undergo transition from subsonic to supersonic or vice versa. So we discussed a situation which had a discontinuity, and the discontinuity is what causes the transition. Across the discontinuity, you will have transition from supersonic to subsonic flow conditions. But if you don't want a discontinuity, what do? You study transonic flows, which are smooth transitions between these two flow conditions. Okay, smooth will mean that you go from situation of m less than 1 to m equals to 1 to m greater than 1. No jumps are involved, unlike shocks. All right. Uh, Now, to study these, let us consider steady flows and situations where the flow of the cross section of the flow will change. So you can consider fluid moving through a pipe, and the pipe will initially, let's say, the pipe tapers off, okay, or the pipe will widen at some point. Such situations where the cross section of the flow will change. In such situations, what is conserved when you're considering mass continuity equation is this quantity rho AU, rho being the density, u being the velocity, and a being the cross section of the flow. This is a constant. The differential form, so if you divide this by dx, what do you get? You get au d rho dx plus rho u dA dx plus rho a du dx equals to 0. Right hand side is a constant. Now you can divide this entire equation by au rho to get this. Okay, we keep it as it is. Then we go to Euler equation, because once again we are studying inviscid fluids, uh, and since we are studying steady flows, this term drops off, and in 1D this will be rho u du dx plus dp dx equals 0. We once again rewrite dp dx as dp d rho times d rho dx. dp d rho is cs square times d rho dx. Okay, we divide this entire equation by 1 by rho cs square, and we get this. Now what happens is we will substitute for du dx. No, sorry. We will substitute for d rho dx in the first equation. We plug back this expression over here and get this. I hope it's clear. You get a 1 by u du dx, which is basically this term. You get a minus u by c square du dx, which is this term. And you had a minus 1 by e du dx left over, which is this. Okay. Now, let us pull out 1 by u from the left hand side to get 1 minus u square by c square equals minus 1 by a dA dx. We cancel this minus 1 and write this as this, which is basically this. This is the Mach number square. Now, this is a very important equation. Why? Because this is exactly what we wanted to know, that if we have such a situation where the cross section of the flow changes, let's say the pipe tapers or the pipe widens, what happens to the flow? Will we have increase in velocity? Will we have decrease in velocity? What will happen to the flow? So this equation tells you that. Also, since u and a, which is the speed and the area of cross section, cannot be negative, they're positive quantities, you can see that if m is less than 1, then m square minus 1 is less than 0. So subsonic flows with m less than 1, will accelerate in converging channels. If this is negative for m less than 1 and this is negative for converging channels, by converging I mean pipes that taper off like this, then du dx is positive. So fluid will accelerate. The, the speed of the fluid at different points will keep increasing as you go along x. So the fluid accelerates. Okay. Similarly, if you're considering supersonic flows, then this is positive. And if you're still considering pipes that are that taper, that are converging channels, then du dx becomes negative. So supersonic flows will decelerate. Du dx is negative for them. So as you go along the pipe, as you go along the flow, you will see that u actually decreases because du dx is negative. And this is very counterintuitive. You would expect that if the pipe tapers off, u should increase. But that's only for a certain flow condition. That's only true for subsonic flows. For supersonic flows, the fluid will decelerate. Okay. And when I say accelerate, decelerate, do not confuse it with acceleration, deceleration in time. These are steady flows. So at a certain point in x, u does not change. It's as you go along x that u is increasing or decreasing. Okay. So what this allows you to do is, without doing much, you can just put together a combination of this convergent and divergent channels, and you can create a supersonic flow condition from subsonic steady flows. This is the Delaval nozzle, and just from this principle, if you start with a subsonic flow, a convergent channel will increase speed, and then once at this point, you would engineer it such that at the throat, the flow conditions start to become supersonic, and then you allow the pipe to widen again. And we know that for supersonic flows, a divergent channel will lead to increase, it will result in acceleration of the fluid. So that's what happens. So you need supersonic flow conditions, starting from subsonic flows. Okay. Uh, and then a few astrophysical applications were discussed where you have, let's say, astrophysical jets, where you can consider compact objects like, let's say, pulsars or some active galactic nuclei. You can have things like blazars and so on, which release jets, and these jets are believed to be relativistic. These are the content of these jets are believed to be relativistic, right? So one of the proposed mechanism is that of this principle, this delivery nozzle. You start off with subsonic flows. When the jet is released, it's subsonic, and then the distribution of ambient matter around the compact particle is such that it will initially face such conditions. You can look at the pressure conditions, the pressure gradient, as a pipe which tapers off. So the flow of the jet particles, the fluid in the jet particles, is looked upon as going through this tapered pipe. So the velocity increases, and then the density of the ambient matter around the compact particle falls off. So you can look at the situation as the pipe widening again, and the supersonic speeds for the relativistic jet is reached. And then uh, another situation was discussed in significant detail, which was the spherically symmetric accretion or emission of matter around an object, right? So accretion would be, let's say, an example would be black hole, or emission would be that of solar wind. But just know that these we are talking about spherically symmetric accretion. So the way these the matter for which we use fluid approximation. So the way this fluid is accreted around this object or is emitted around this object, rather away from the object, is spherically symmetric, which is to say that the only changes in the flow profile are that of DDR. DD theta and DD phi of whatever parameters are zero. Okay. So if you remember, the way we derived the jump conditions, we will repeat exactly the same steps to get some equations for this spherically symmetric accretion or emission. The mass conservation equation will now look like this because previously, remember, this quantity was conserved, but now A would be the area of a sphere proportional to which is proportional to r square. And then once again we divide this by ddx, but now we are working in in spherical coordinates, so ddx is nothing but ddr. dd theta, dd phi are all zero. So performing ddr of this equation will give you this, and 1 by r square ddr of r square is nothing but 2 by r. So this is the mass conservation equation for this situation. And then we consider momentum conservation. But now we cannot ignore body forces because we're dealing with very massive objects. We're dealing with the sun or a very heavy, let's say, uh, galactic nuclei. So these are very heavy objects and body forces cannot be ignored. So we write down a body force term and the other terms in the Euler equation. Once again, we are dealing with steady flows. So this term drops off. Okay. And we write down this equation. Once again, DDR is the only derivative that is non-zero. So this term becomes this term. This is dPdr and G is Gm by r square. Okay. Once again, dPdr we write as del P del rho, d rho dr, and del P del rho is written as C square. Uh, and this equation is rewritten as this. Okay, what we do is we will use this expression of 1 by rho d rho dr in the previous equation, and this then becomes this equation. Okay, all right. Uh, then we multiply this entire equation with Cs square. So we get du dr Cs square by u minus u equals to minus 2 Cs square by r plus Gm by r square. Okay. Then we take minus sign common from both sides and we get this. Okay. So what we wanted to do was we wanted to look at transonic solutions, transonic flow solutions of this accretion or emission. And transonic solutions will always pass through Mach number one flow conditions, Mach number one conditions. Uh, that's what transonic means, because you need to have a smooth transition, and if you need to have a smooth transition, at some point you will cross Mach equals one. At some r, at some at some point, by at some point I mean uh, mm, at some value of r. So, but you see, there's a problem over here, because this term will move to the denominator, but this term is essentially u square minus cs square, and at Mach equals 1, this is 0. So the denominator is 0. This means that du dr blows up. But if du dr blows up, it can't be a smooth transition between flow conditions. So what do? We have to demand, if it has to be a smooth transition, then we have to demand that the numerator is 0 as well. Because then we have a 0 by 0 form. We can then use L'Hopital conditions to know what du dr is at the point where we have Mach equals 1. And then it will be finite, it won't blow up. Demanding that the numerator be 0, we get this value of r, and this is the value of r at which we have smooth transition from subsonic to supersonic flow conditions. Okay, so this concludes revision of the material that was covered this week. I will proceed to sample assignment problems if there are no more questions. Okay, let me proceed then. All right, we have to choose the correct options. There are 4 options given. In real life, the thickness of a shock front is much less than the mean free path of the gas particles. Is this correct?
False.
That's correct. That's right. Because we discussed that the thickness of the shock front, we considered a real life situation where the shock front is not thickness is not exactly 0, and it's not an ideal discontinuity. And we saw that the thickness could be related for at least for uh, not really large supersonic flows, for mildly supersonic flows that are steady. We saw that the thickness of the shock front is comparable to the mean free path, which you will see is option B. So A is false, B is correct. Okay. The third option is the term involving Laplacian of u in the Navier-Stokes equation is negligible near the shock.
False.
That is correct. Once again, correct. That is because near the shock, just so that we're all on the same page, near the shock, you have really large jump. Well, I shouldn't say really large jump in u, but what really matters is the jump in u occurs over a very small length scale dx. And what you're doing is you're considering dx2. So this is even larger than du dx. So this quantity, the Laplacian of u, becomes significant when you're considering any sort of changes in u over very, very small length scales. So this is not true. Okay, the fourth option is a shock results when the forward and backward characteristics cross each other. So if you remember the method of advection equations, method of characteristics, we considered the conservation equations, and we said that we combined those equations and we derived a few equations that told us that certain quantities are advected, so they are transported unchanged along forward and backward waves, right? And we used these, we had these graphs, right? So this was the forward wave, this was the backward wave, and we said that, well, if we want to derive the flow conditions at a point P, what we will do is we will find out the forward wave that traveled to P and the backward wave that traveled to P by drawing lines that are parallel to the forward and the backward characteristics. And we know the flow conditions in the beginning, before the system was perturbed, before, let's say, the piston was pushed, or let's say before the mm, sheet dividing two regions of two different pressures was punctured. Hmm. Uh, and that is how we could derive the flow conditions at P at some future time, at some time T. This gives us a unique solution. This allows us the fact that certain quantities are transported or advected, they remain unchanged along these lines. This allowed us to solve for unique flow conditions at this point. But so if it's a unique value, if it's a unique solution, there's no question of discontinuity. Remember, the discontinuity arose because we could not explain this sort of profile. We could not explain how the pressure at a certain point can have three different values. If it's a unique solution like this, then there's no problem. Then there's no shock. The question of getting two or three different values at the same point uh, will arise when, let's say, two forward characteristics will intersect. Let's say you had a forward wave traveling from this point to P. Let's say you have another forward wave traveling from this point to P. That can happen because the velocity of these two waves are different. That's precisely why this pulse was changed to such a profile. When that happens, you have some conserved quantity traveling from this point to this point, from this point to this point, and you have some conserved quantity traveling from this point to this point. But these two quantities are different. Now you don't know which one is true. That's exactly what happens here. Hmm. So a shock will not result when forward and backward characteristics cross, because this crossing is exactly what we use to find out flow conditions at a point. But a shock will result when, let's say, two forward characteristics cross or two backward characteristics cross. Okay, all right. So moving on to the next question. Uh, yeah. So the correct option is B. All right. Next question is mathematical. Let's say we have a wave equation and we have another wave equation. Well, I wouldn't call this is not a wave equation. We have another equation. This is an equation for the quantity f. This is an equation for the quantity g. Now, if these are true, how can f and g be possibly related? These are the options. F can be r times g. F can be 1 by r times g. F can be r square g. F can be 1 by r square times g. Now, the only way to find it out is actually take this equation, take these possibilities, plug it over here, and see which one gives you this. Hmm. So let me tell you what the correct option is, and you can try with other options as well. You will see that the correct option is this. So if you take f as 1 by r times g and compute the Laplacian, which in spherical coordinates is 1 by r square, del r of r square del f del r, and just go through the steps, you will see that it's this, right? So on the right hand side, you have c square grad f, the Laplacian of f, which is c squared by r del 2g del r2. And on the left hand side, you have del 2f del t2, which is del t2 of g by r. R is just taken out and r cancels. And that gives you this equation. Del 2j del t2 equals c square del 2g del r2. So the correct option is B. All right. Next question. Consider a shock formed in an ideal gas of some finite temperature T. Now you have to choose the correct option, assuming that the speed of the gas flow remains unchanged across the shock. Okay. The first option is the shock may disappear if the temperature of the gas is increased sufficiently. Any guesses? So if the temperature of the gas is increased, what increases? If you remember Cs square, which was del P del rho, assuming barotropic fluid was gamma P by rho, but P is some nkt. So if T increases, the speed of sound increases, right? Now, if the speed of sound increases, what happens to the Mach number? The Mach number, which is U by Cs, what happens to it?
Decreases.
Absolutely, because we know that the speed of gas flow remains unchanged across the shock. So Mach actually decreases as the temperature increases. Now, if across the fluid, Mach keeps decreasing, after a certain point of time, as you keep uh, increasing temperature, Cs will decrease sufficiently. Oh, sorry. I think I'm wrong. I think I'm wrong. Sorry. Yeah. Cs will increase sufficiently such that the Mach goes down below 1. Can you have shocks in subsonic flows?
No.
Absolutely. So you might see that the shock will disappear if you keep heating the fluid. If you increase the temperature of the fluid above a certain point, the flow conditions become subsonic, and then the shock will disappear. Is this clear? Okay. The second option is the shock thickness will decrease with increasing T.
No, because the temperature will increase the mean free path, and mean free path increases means the shock thickness will also increase.
Absolutely. Absolutely. You're right. You're right. And that is also related to the disappearance of the shock. As the shock thickness increases, the discontinuity stops being a discontinuity, right? Uh, and the change becomes continuous. You see what I'm saying? Okay. So B is not true. The pressure behind the shock will increase with increasing T. Okay. So let's do this. With increasing T, Mach decreases. Now if I go back to the plot where we plotted the jump conditions with respect to Mach number, we see that as Mach number decreases, which is what happens when we increase temperature, what happens to this jump condition? It decreases, right? So, wait, this is not the right question. So this is false. Is this clear?
Can you just come again?
Yeah. So with increasing T, the Mach number decreases.
Okay.
Now, by behind the shock, what is the zone which is behind the shock? It is the already shocked part.
Okay.
That's correct, right? Because the zone that is uh, in front of the shock is the unshocked fluid. The fluid which is behind the shock, the zone which is behind the shock, is the already shocked part,
Okay.
right? Now,
Hmm.
the already shocked part we denote by the subscript 2.
Okay.
And that plotted against the Mach number, we see it decreases with decreasing Mach,
Okay.
right? So, with increasing temperature and decreasing Mach, P2 actually reduces.
Okay.
So, so this option is false.
Okay.
Okay, so the only true option is A. All right. Next question. Uh, for an ideal normal shock, ideal would mean that you have an ideal discontinuity. The normal component of velocity is continuous across the shock.
No, there is a discontinuity.
Absolutely. Absolutely. No, no, wait. The normal component of the. Sorry. Normal is the component that is perpendicular to the shock surface. So if this is the shock surface and this is the normal component, uh, it is continuous across the shock. That's absolutely true. There's a
Okay.
discontinuity. Right. Okay. Related to this option is D. So let's read that first. The tangential component of velocity is continuous across the shock.
Yes.
That is true. That is the definition of normal shock. So what we have done is we've defined normal shock as, let's say this is the shock front. This is the surface of the shock. Uh, U tangential, rho tangential, P tangential, these are all continuous. These do not suffer any discontinuity across the shock front. But as we go from one side of the shock to another, the normal component of these parameters, they are discontinuous. That is how we have defined normal shocks. You can also have oblique shocks that were not discussed. Uh, but yeah, so this is true. This is not true. Okay. Now, for ideal monoatomic gas, whose gamma is given, the density jump across the shock cannot exceed a factor of 4.
Mm,
Any guesses?
it was a Mach number 4, right? It was not the density jump.
So, if you look at this, uh, what were we referring to? Sorry, yeah. So, the for ideal monoatomic gas, density jump across shock cannot exceed a factor of 4. Now, if you look at this density jump plotted across Mach number, it is true that after a Mach number of 4, it sort of asymptotes. But it is also true that rho 2 by rho 1, this jump does not even exceed a factor of 10, let's say. Now, it is since it's log scale, it is slightly difficult to say what this number is because it's something between 2 to the 2 to 3. Yeah. Uh, so this is 1, right? So this has to be point 0.2, zero point 0.4, zero point 0.6, zero point 0.8. Yeah. So it's somewhere between zero point 0.4 to zero point 0.6. So it's somewhere between 10 to the power of 0.4 to 10 to the power of zero point 0.6. Now, one can compute this, whether this is greater or lesser than 4, uh, right? Since I don't have a calculator with me right now, apparently this is true. So feel free to check. But yeah, so all you have to do is this. It is indeed true that a Mach number of 4 is considered to be what would infinite Mach number flow or something, right? If you remember. That's because you look at how the jump in rho and v looks like, and you see that it does not matter whether Mach is 10 or 10 to the power of 5. Rho 2 by rho 1 will be the same. You cannot produce a greater jump in density and velocity by simply increasing the Mach number indefinitely. The jump will be the same number. be careful, because a lot of now from now onwards, once you're moving to astrophysical situations, you will have log scales. So be careful of that. Check for log scales anytime you see a plot. Um, okay, all right. Uh, okay, so one more thing is we don't even have to worry so much about where did this plot go? We don't even have to worry about finding this number. Look at this. Look at this equation. Hmm. Now what you can do is you can find out rho 1 by rho 2. Have I written it somewhere? Let me see. Uh, okay, I think I haven't, but you can find out rho 1 by rho 2 from here, right? So this will be what? This will be 2 by gamma plus 1 Mach square plus gamma minus 1 by gamma plus 1. Now, what one can do is the Mach mentioned in that question? Yeah, so take Mach to infinity, because we are saying that it cannot exceed a factor of 4. So take Mach to infinity. I'm so sorry, I lost it. I think. Yeah, take Mach to infinity. So this term is 0, and then substitute gamma equals 5 by 3 and see what we get. So gamma minus 1 is 2 by 3, gamma plus 1 is 7 by 3. Rho 2 by rho 1, this which is the actual jump, because rho 2 is the behind the shock, the rho 1 is in front of the shock. This is what? 7 by 2. This is less than
3.5.
4. It's less than 4.
Yeah.
So it cannot exceed 4. And hence this option is, where is it? And hence this option is correct. This option is correct. Okay, the enthalpy of the gas is conserved across the shock. This is not true. And this is not true because if you remember, when we derived the jump conditions, we derived jump conditions for, let me erase this. So you see that we have jump conditions for density and we have jump conditions for the pressure, right? And what is enthalpy? It's this. So gamma will remain constant across the shock front, but you have W1, which is P1 by rho 1, that is different from P2 by rho 2. So enthalpy does change across the shock front. Okay, is that clear?
Actually, is it proper to call it enthalpy, or should it be more appropriately called the specific enthalpy? Because we are talking about the enthalpy per
Specific
unit mass.
enthalpy. You're right, specific enthalpy. Yeah, okay, good, very good. All right. Now consider an ideal gas passing through the de Laval nozzle such that the flow transitions smoothly from supersonic to subsonic. Okay. One can also use this setup to have a flow transition smoothly from subsonic to supersonic.
True.
That's true. That's true. Because just like we had, just like we started from, what is it? Just like we started with m less than 1, if we had started from, oh yeah, from supersonic to subsonic. So to go from supersonic to subsonic, you start with m greater than 1. Similarly, if you start with subsonic, this convergent column will tell you that your flow, the velocity increases. It starts transitioning from subsonic to supersonic, and once again it places a divergent channel over here. Then it's properly supersonic over here. Okay, so it is indeed true that you can use the same setup to have a flow smoothly transition from subsonic to supersonic. So option D is automatically disqualified because it says that it is not possible to have this transition. So this is false, this is correct. Okay, if the flow passes smoothly through the critical point being the sonic point where n exactly equals to 1, then there cannot be a shock.
True.
Absolutely. That's what shock means, and that's exactly what smoothly passing through means. This is true, which
and C
means
is
that
false.
this is false. Absolutely. Uh, that's it. And if you have any questions, ask. Otherwise, this is all that I wanted to talk about. This ends this week's lectures. We have mostly covered everything from this week's lectures. And if you have any questions, then ask. Feel free to leave them. I'll end the recording here.